Good afternoon, students. So today in the Unit 11, we are going to see the next topic, that is the characteristics of the stationary waves. So stationary waves are characterized by the confinement of a wave disturbance between the two rigid boundaries. So this means the wave does not move forward or backward in a medium. That means does not advance. It remains steady at its place. Therefore, they are called stationary. So, generally, you know what is a stationary, right? So, it is at the same place. So, same like that, the waves do not disturb by the medium. So, that's why it was remain at its same place. That means it does not move forward or backward. Between the two rigid boundaries, it will be at the remains at the steady place. So that's why it's called as in standing waves or a stationary waves. This is the first characteristics of this stationary waves, and the many things will be given for the comparison way they are given. So what is a comparison between the progressive and the stationary waves? So progressive means crest and troughs are formed in the transverse progressive waves, and compression and rarefactions are formed in the longitudinal waves. You know that. So these waves are move forward or backward in the medium. So we know that the longitudinal wave or in the transverse waves both will be moving right in the air medium, because it will disturbs the air medium, disturbs the particles to move forward or backward. So it's a well advanced one with a definite velocity. But stationary waves, what happens to the stationary waves means the crest and troughs are formed in the transverse stationary waves, and the compression and rarefactions are formed in the longitudinal stationary waves. These neither move nor forward in a medium. Same thing. So it is at the same place. They will be not advance in the medium. So for the progressive wave, all the particles in the medium vibrate such that the amplitude of the vibration of the particle is same. So what happened means all the particles will be vibrate in the air medium in progressive way, but here except at the nodes all the other particles of the medium vibrate such that the amplitude of the vibration is different for different particles. So except the node, all the other particles only the make a vibration. So this will be different amplitude for the different places. So the amplitude is minimum or 0 at the nodes and maximum at the antinodes. We already know what is a node and antinode. So in that node place it will be minimum or maximum the amplitude, but antinode place it will be different. Okay, that means maximum. And then in progressive waves, these waves carry energy while propagating. So in the propagation, the energy will be taken place by the wave, that is it carry the energy, but here no transport of energy where the stationary waves. So these are all the difference and also the characteristics of the progressive wave and also the stationary waves, but here that will be given as a comparison. So it's a very important one. Okay. And next, we are pass on to the next characteristics of the stationary wave. Certain points in the region in which the wave exists have maximum amplitude. So same thing whatever we did discussed in the comparison, same, though it will be maximum amplitude at antinodes and minimum or 0 in the nodes. So distance between two consecutive nodes and antinode, that will be discussed in the last derivation. So what is the difference of the two means the lambda by 2 for the node and also for the antinode. So distance between a node and the antinode for the neighboring antinode means that is a lambda by 4. So transfer of energy along the standing wave is 0. Okay. So these are all the characteristics of the standing wave and or a stationary wave. Next we pass on to the stationary waves in the sonometer. So sono means you know that it's a sound related one. Sonometer implies sound related measurement. So it is the device for demonstrating the relationship between the frequency of the sound and produced in the transverse standing waves in a string. So when you are tried a string and if you make a vibration, it will produce some sound. Okay, and that frequency producing frequency, that sound producing, no, that frequency only we are telling that as a measured by this sonometer. So yeah, the tension and the length and the mass per unit length of the string, everything will be measured with this sonometer. So using this device we can determine determine the following quantities. So what are the quantities means? First we are able to find out the frequency of the tuning fork or frequency of the alternating current or the tension of the string, and then the unknown hanging masses we are able to find out with this sonometer. So what is the construction of this sonometer is? Sonometer is made up of a hollow box which is 1 meter long with a uniform metallic thin string attached to it. One end is connected with the hook and the other end will be connected to a hanger. So it is like this. Okay, so the sonometer diagram is given here. So one end is connected with that and other end will be connected with the load. So we are giving a different load for finding the different frequency and finding the different tensions. Okay, and we are able to know the mass of the load also. So that is the sonometer. And then what is the next thing has to be given? So it's through a pulley. So since only one string is used, it is also known as monochord. If we are using only one means that is monochord. The weights are added to the free end of the wire to increase the tension of the wire. So two adjustable wooden nails are put over the board and their positions are adjusted. So this is the adjustable nodes P and Q. No, these two are adjustable nodes. So this will be giving the different adjustments for this strings. Okay. And that is given here. And what happened to that means if you are adjusting, and that will be changing the vibrating length of the stretched wire. So what is a working of it means? A stationary or a standing wave is produced, hence at the knife edges P and Q nodes are formed. So in between the knife edges antinodes are formed. So at the edges nodes will be forming and between the edges antinodes will form. So if the length of the vibrating element is L means L is equal to lambda by 2. So what is lambda? Lambda is equal to 2L. Okay. And frequency we know that V by lambda. So V is equal to, so that's why we are substituting the value. So we will get 1 by 2L root of T by pi d square rho by 4. Okay. So finally we are getting the frequency as 1 by LD. T by T is a time period. Pi and rho is a density. Okay. And pi into rho. So this is the frequency of the whatever the strings we are using, that frequency producing, sound producing, you can see. Okay, so these are all things for the sonometer. So it's a very easiest one. And next we are pass on to the next topic, that is fundamentals, frequency and overtones. Okay, fundamentals of frequency and overtones. Frequency and overtones means let us now keep the rigid bodies boundaries at x is equal to 0 and x is equal to capital L. Now it produces a standing waves by feeling the string. So that means plucking the strings in the guitar, no, like that. So standing waves with the specific wavelengths are produced. So amplitude must vanish at the boundaries. Therefore the displacement at the boundary must be having the following condition, that is y is equal to x is equal, y of x is equal to 0 comma t, that is equal to 0, and also the y of x is equal to L comma t, that's equal to 0. That means nodes are formed at the distance of lambda n by 2 and we have n into lambda n by 2 is equal to capital N. N is an integer and capital L is a length between the two boundaries, and lambda n is a specific wavelength that satisfies the boundary conditions. So lambda n is equal to 2L by n. Okay, so therefore not all the wavelengths are allowed. The wavelength should fit the specified boundary conditions. That is, for n is equal to 1, the first mode of vibration has a specific wavelength, lambda 1 is equal to 2L. So when you are substituting n is equal to 2 means second mode of vibration has specific wavelength. That means lambda 2 is equal to 2L by 2. Same thing you will get as a L. For n is equal to 3 means we are substituting n is equal to 3. That's why we are getting that 2L by 3, and that will be going on up to the n values. And then the frequency of each mode of vibration, that is the natural frequency, can be calculated. Okay, so we have Fn, what is a frequency, that is for the n values, that's equal to V by lambda n, that is n into V by 2L. So the lowest natural frequency is called as an fundamental frequency. So which is a very lowest frequency, that is called as a fundamental frequency. For that, if now we are going to substitute the different values of L. Now first we are substituting n is equal to 1 means, so that's the first overtone, that we will get F1 is equal to V lambda V by lambda 1, that's equal to V by 2L. And second natural frequency is called as an first overtone, and that will be F2 is equal to 2 into V by 2L, that we will get 1 by L into T by mu. Mu is a frequency. Okay. We are having the frequency F2 is equal to 1 by L root of T by mu. The third natural frequency is called the second overtone. So for that 3V by 2L, that is 3 into 1 by 2L, V value is T by mu, and so on. For the nth natural frequency, so as computed as an integral or the multiple of the fundamental frequency. So first fundamental frequency we are getting, no, that multiples will give the nth natural frequency. So Fn is equal to n F1. So where n is an integer, if natural frequencies are written as an integral multiple of the fundamental frequencies, then the frequency are called harmonics. So it's a very important word, mark it. So first harmonic is equal to F1 is equal to F1. That means we are substituting n is equal to 1. And then second harmonic F2 is equal to 2F1. That's why we are substituting n is equal to 2, like that for the n multiples of harmonic we are getting. So third harmonic, that is F3 is equal to 3F1. Okay. So these are all the fundamental things, frequency and then the overtones. Okay, different tones. And next we pass on to the next thing, that is laws of transverse vibrations in stretched strings. 3 laws of transverse vibrations for the stretched strings which are given as: first, the law of length. For the given wire, what is a tension, which is fixed one, and the mass per unit length, that is mu, has to be fixed. The frequency we make fixed, and then frequency varies inversely with the vibrating length. So inversely varies means, so F is inversely proportional to length, so that is 1 by L. So F is equal to C by L. C is a constant one. Okay, so what is C is equal to L into F. So this is a first law. And then second law is a tension, that is a law of tension. So for the given vibrating length, L, now L is fixed and mass is fixed. Now the frequency varies directly with the square root of the tension. So F is proportional directly to the T. So F is equal to AT. Here A is a constant. Next law of mass, same here also, the length is fixed, tension is fixed, and now we are going to inversely, that varies inversely with the square root of the mass per unit length. So in law of mass, which has to be a fixed one, length is a fixed one and tension is also fixed. So it's inversely the square root of the mass per unit length. So that is equal to F is proportional to 1 by root mu. So that is equal to B by root mu. Here B is a constant. So this is the 3 laws of the transverse stretched string. So what happens means, we are fixing two things and we are taking the another thing. So like that, the proportionality will be taken place for everything, for the law of mass, law of tension, and also for law of the length. Next we pass on to the intensity and the loudness. What is an intensity and what is a loudness? We are considering a source and the two observers, that is the listeners. The source emits the sound. If I am the source means I am emitting the sound which carry the energy. So the sound energy emitted by the source is same regardless of the whosoever measured it. Okay, so it is independent of any observer standing in that region. But the sound received by the two observers may be different. This is due to the some factors like a sensitivity of ears. To quantify such thing, we can define two different quantities known as intensity and sound, loudness of the sound. What is the meaning of it? If I am producing the sound, you are all the students. Okay, so different students are sitting here. So you are all receiving my voice, but one will receive more clearly, that means more higher voice, and the other one will be very less voice they are receiving. So what that thing means, it is maybe a here sensitivity, but the two things will be differentiating this two. What is the two things is, one is intensity, other one is a loudness. So what is first intensity? When a sound wave is emitted by a source, the energy is carried out to all the possible surrounding points. The average sound energy emitted for the transmitted for per unit time or per second is called as a sound power. That is, intensity is nothing but how much the power of the sound, that is the intensity. So the sound power transmisses per unit area taken normal to the propagation of the sound wave, that is the intensity. Okay, so here it is clearly given in the diagram. Sound source on distance 1 and then distance 2, distance 3, and it will be reaches, and like that the sources will be for the different distance. Okay, this is the intensity of sound waves. So for particular source, that means a fixed source means the sound intensity is inversely proportional to the square of the distance from the source. That means I is equal to power of the source by 4 pi r square. That is, I is proportional to 1 by r square. This is known as inverse square law of the sound intensity. Very important one, inverse square law. Next we pass on to the loudness. Two sounds or with the same intensities need not have the same loudness. For example, sound heard during the explosion of balloons in the silent closed room, it very loud. You know that you are blasted the balloon, no? So you know what is the sound of it. When compared to the other same explosion happening in the noisy market, though the intensity of the sound is same, but the loudness is not. If the intensity of the sound is increased, then the loudness also increases. But additionally, not only does the intensity matter, the internal and the subjective experience of how loud a sound is, that is the sensitivity of the listener, also matters here. This is called loudness. So when the loudness depends on both the intensity of the sound wave and the sensitivity of the ear. So you know, so if intensity means it depends on the sound, how it is, how it was produced, and how it was passing through it, like that. But the mainly the distance makes the intensity, but the loudness is for the two things. It depends, one, how much sound we are producing, that intensity, and also the sensitivity of the ear will depends on the loudness. Okay, so that is the loudness, whereas the intensity of the sound does not depend on the observer. So the loudness of the sound is defined as a degree of sensation of the sound produced in the ear or the precision of the sound by the listener. So next we pass on to the intensity and the loudness of the sound. Intensity and the loudness of the sound. So if you can detect the sound with the intensity, means that ranges from 10 to the power of minus 2 Weber per meter square to 20 Weber per meter square. So it's according to the Weber-Brencher's law. So the loudness L is proportional to the logarithm of the actual intensity I measured with an accurate non-human instrument. This means L is proportional to the Ln is nothing but the natural logarithm. So that is I. So L is equal to K ln I. So K is a constant which depends on the unit of measurement. The difference between the two loudness L1 and L0 measures the relative loudness between the two precisely measured intensities called as a sound intensity level. So del L is equal to L1 minus L0, that is equal to K natural logarithm of I1 minus K natural logarithm of I0, that is K natural logarithm I1 by I0. When K is equal to 1 bell, K is equal to 10 decibel, then the sound intensity level is measured in bell because the honor of the Alexander Graham Bell. So del L is equal to natural logarithm of I1 by I0 bell. So but practically it's a bigger unit, so we are conveniently using a smaller unit called a decibel. So 1 decibel is equal to 1 by 10 bell. So multiplying dividing by 10, we will get del L is equal to 10 of natural logarithm of I1 by I0 1 by 10 bell. So then means del L is equal to 10 natural logarithm of I1 by I0 decibel with K is equal to 10. So for the practical purpose, we are using the logarithm to the base of 10 instead of natural logarithm. So we are writing that del L is equal to 10 log of base 10 I1 by I0 decibel. We are using this for the what purpose we are using that? We are using that in the purpose of practical. Okay. Next we pass on to the vibration of air column. So we know that the musical instruments, flute or clarinet or nathosferum, etc. is known as a wind instrument. They work on the principles of vibration of the air columns. So the simplest form of the wind instrument is an organ pipe. So it's made of the wooden or the metal pipe. You all know that, right? Organ pipe, which is produce a musical sound. For example, flute. flute, we are just closing and opening the holes, we will receive the sound. This is mainly due to the air. Okay. Clarinet, same like a Nadaswaram also, or the organ pipe instruments. Organ pipe instruments are classified into two pipes. One is a closed organ pipe and the closed organ pipe. So look at this picture of a clarinet. It shows, okay, here this is a clarinet and this is a closed organ pipe. So if it is a pipe with one end closed and the other end open, if one end is of the pipe is closed, the wave reflected at this closed end is 180 degree out of phase with the incoming wave. So there is no displacement of the particle at the closed end. So like this, they are given this as a diagrammatically how it was moving. Okay. So if therefore the nodes are formed at the closed end and antinodes are formed at the open end. See here. So the nodes are formed at the closed end. This is the closed end. So it forms the nodes at the closed end, and in the open end the antinodes are formed. These are the antinodes. Okay. So like that, when you are giving the air to it and it produces a sound, it will be forming the nodes and antinodes. Let us consider the simplest mode of vibration of the air column called the fundamental mode. So the antinode is formed at the open end and nodes are at the closed end. So L be the length of the tube and wavelength of the wave is produced. So fundamental mode of vibration, we know that capital L is equal to lambda 1 by 4. So lambda 1 is equal to 4L. So frequency of the note is emitted, that is F1 is equal to V by lambda 1, that's equal to V by 4L, and which is the fundamental note. So frequencies higher than the fundamental frequencies can be produced by blowing as strongly at the open end. Such frequencies are called overtones. Okay. So second mode of vibrations having the two nodes and antinodes, and that will be for the which we have for from the example. So that is also given here how it was look like. So 4L is equal to 3 lambda by 2. So L is equal to 3 lambda 2 by 4. That is lambda 2 is equal to 4L by 3. So that is frequency. Nu is equal to lambda by lambda, that is lambda by 2. So 3 V is equal to V by 4L. So it's a first overtone, and the frequency for the 3 times the fundamental frequency, that is a third harmonic. Okay, so this shows the third mode of vibrations having 3 nodes and 3 antinodes. Same for the diagram also given. And the next is fourth for 4L. So 5F lambda 3, that is 5 lambda 3 by 4. So lambda 3 is equal to 4L by 5. So it's called second overtone. So N is equal to 5 means it's a fifth harmonic. So the closed organ pipe has only the hard harmonics, and the frequency of the nth harmonic is equal to Fn is equal to 2n plus 1 F1. That is in the frequency of harmonics, or in the ratio of F1 is to F2 is to F3 is to F4, like that it will be going on. Closed organ pipe, let us consider the picture of the, so it is a picture of the flute. So now we are going to consider this picture, and it is a pipe, both ends are open. Correct, both the ends are open. So at the open ends, antinodes are formed. Let us consider a simplest mode of vibration in the air column called fundamental mode. So antinodes are formed at open end and nodes are formed at the closed end. So what happened? L be the length of the tube, wavelength is produced. So L is equal to lambda 1 by 2 and lambda 1 is equal to 2L. So frequency mu is that is V by lambda 1, so V is equal to by 2L. So it's a fundamental note. So frequencies higher than the fundamental frequency can be produced by blowing as strongly at one end of the open ends. So such frequencies are called overtones. Okay, so it's a second mode of thing. And second mode means it has 2 nodes and 3 antinodes. So L is equal to lambda 2, lambda 2 is equal to L. Frequency F2 is equal to V by lambda 2, that is V by L. The 2 into V by 2L, that is equal to 2 F1, that is first overtone, and N is equal to 2. Here it is a second harmonic. So for the third mode of vibration, so 3 nodes, 3 antinodes, same thing we will get lambda 3 is equal to 2 by L. 2L by 3. So frequency 3F1. So it's a second overtone. N is equal to 3. It is a third harmonic. Okay. So like that it will be going on. So here we are getting the different values for the F. Okay. So understand these things, vibrations in the column. So the up to this you are having this unit. So this unit is over. So up to this you are having a portion for your oral examination.